Okay, morning everyone. Let's begin today's portion of the lecture. It's good to see everyone again. So, what we're going to do today, let's first have a review of what we have taught the last class, okay? We taught everybody about some of the basics in free joined chain. This is a very, very basic example about chain conformation. So we start with something fundamental, understand how free joined chain you can correlate to end-to-end distance with a very simple formulation, how you RE will be correspond to average square can be simply written as NL square, right? And we know what is N is and L is in each this equation. We use the polyethylene as example, 280K, and we actually checked what is the end-to-end distance. So in today's lecture, we're going to do something a little bit more realistic. So in the last lecture, we talked about free joint chain, but that's a little bit too simplistic, although it's a good starting point. Like when you get into any sports, there's also an entry level setup, right? So this is the entry level. So today we're going to talk on two more examples along these lines. Those two examples are free rotation chain. In this case, we're going to give a little bit of restrictions on what free rotation chain to hinder the rotation chain, or sometimes we call rotation isomer chain. So those two are very similar concepts. So let's start from here. So this is where we talked about in the last lecture. We talked about what are the vectors are, how we can use a vector to simply link all the bonds into what is the final end-to-end distance. So your end-to-end distance, RE, will be equals to all the bond vectors connected, L1 plus L2, plus all the way to Ln. So this is a great example. So in today's lecture, in the last lecture, basically we told you that in the free joint chain model, let's right here. So we're going to have a spec comparison. That's right, free JC is free joint chain. In this case, we have several parameters. The length of the bonds as L, and we have the bond angle and rotation isomer angle phi. Okay, so in this, L is fixed in the first model, but this is free, and this angle is free. So we don't have any restriction, right? And we know the end-to-end distance RE will be equals to NL squared. So today's lecture, let's begin with free rotation chain. So what's the difference between free, F stands free, rotation chain with free joint chain? If you can see it, I can probably write it one more time so that the students on the side can see it. Just a little bit compact, but the same content, okay? This is going to be free, then you have RE squared. Okay, now I hope everybody can see it. So what about a little bit more realistic? A little bit more realistic would be, let's fix this beta angle, okay? Let's fix the beta angle so that it's represented to sp3. So bond length, again, it's going to be fixed. But now we're going to fix the second one, fix the gamma value, okay? But we still say we have free rotation in the phi. So in today's lecture, we're going to understand, once we fix the angle, how this impacts the end-to-end distance. Will your polymer coil be expanded or contract? and how big expansion will be. So how many of you think it will be expanded? Half of the class? How many you think the end-to-end distance will shrink if you have fixed angle? I see 2. So some of you haven't get your morning coffee yet, I guess you still a little bit sleepy. That's fine. I'm going to help you guys understand. That's the goal of today's lecture. If it's shrink or if it expand, let's understand how big that is. And there's a significance in that expansion factor, and we're going to talk near the end of it, okay? So we have already covered those two, right? So I think the cable has some issue. Let me make sure we don't bend it. And oh no. Let's try one more time. I think we might need an IT person to come fix for next class. Okay, if it doesn't come back, that's fine. We can, okay, why don't we, that's a problem. You know, I'm not equipped to teach you guys how to fix this. So let's stay at that screen, don't move it. We're good for a couple seconds. That's good. So let's come back here. Is it okay? Everybody can see it, or it's too challenging? I think it's a little bit annoying. It's flashing, but let me try one more time. See if we can get this totally away. Unplug and plug one more time. Okay, no, I promise I won't touch that except swipe back and forth. Oh, let's stay at here. So that's today's lecture, free rotation chain. So with free joint chain, in the last lecture, this is where we will arrive at. We have a self term, which means Ri dot Ri, which is dot product of self. So which this term basically comes to where Re equals to NL squared. And we also arrived at a conclusion. When I equals to 1 to n, j not equals to I, Ri dot product Rj, all the angle terms going to average out, because in the free joint chain, the chances of you find a chain pointing to the north is equally to the south, because there's equal probability in all directions. So this term was 0. But now, in today's lecture, we will need to do something with it, because it's no longer going to be 0 if we fix this bond angle. We know Ri dot product Rj is not going to be equal to 0. So how do we address this problem? In the previous few lectures, I like to go into, in previous several years of lecture, I like to go a little bit into the math, but later on it may not be necessary. So I found a perfect solution. If you're interested to learn a little bit deeper in the math, I will post some optional video for you to learn how to derive these terms into this particular, which we're going to talk about just in a second. But if you just feel you're not interested too much in understanding math, but understanding the physical meaning of it, stick with what we talked in the class, okay? So, but there's one thing quite clear. In the free rotation chain model, Ri dot Rj doesn't vanish for I not equals to j, but it decreases rapidly as I minus j absolute increase. What does that mean? Okay, let's talk a little bit physical term. We know what is I minus j is, right? I minus j absolute is basically tell you I have a bond I, next y going to be I plus 1 and I plus 2. which means when your chain has a certain memory, the next one has some certain memory of previous one because it can rotate it around, but the dot product basically says how much this bond has projection along this line. So dot product would be correspond to I plus 1 cosine beta. So this is where the dot product is. But if you keep increasing, the next one going to be rotated around. The dot product of this is going to be equals to cosine theta squared, right? So let's write just a general. So let's say, how do we write a general term, which is Ri dot Rj vector dot product will be equals to L squared cosine beta I minus j absolute power. Okay? So that's how much terms has left. As we know, cosine theta will be between 0 to 1. Because cosine theta is just going to be smaller 1. If you have I minus j is 2, that means cosine theta squared. It's going to be smaller than cosine. If you have cosine theta power of 3 and 4, it's just going to drop pretty rapidly, right? So which means the longer the chain it is, the future the bond is going to forget where it comes from. Pretty like genetics. If you have, if you're coming from, like me, from the Asian family, if I have a kids, the longer generation, the mixed, he's going to lose the, the Asian appearance or something like that. But this is similar. The longer the chain is, it will lose the directionality for the previous bond. So in the long chain, if you count 10 bonds from now, it can point many directions. But if you point just 2, 3 bonds, it will have some ability to memorize what is previous bond effect. And this is given by this particular term. Okay? Cosine depends on its bond angle, depends on I minus j. I minus j is just the distance from bond I to bond j. Okay? If I equals to 1, j equals 2, that means they are neighboring. If I equals to 1, j equals to 10, that means 9 bonds apart. Okay? So, if you're interested to know the math, how to do all the integration, I'll post a video. But for the sake of today's discussion, we will simply arrive there. If you take a limitation, take an approach to approach its limit, when I equals I integrate to n is equally big, you will arrive at this particular equation. So the self term is still here, NL squared, which is defined by the self term. Nothing changes, but the cross term can be written as this particular equation. Okay? And if you could look at the Professor Larger's textbook, it also gives the same explanation. And I'll post a video as I mentioned, okay? So, but how do we add them together? So we basically can add this equation together with this one. You would have NL squared plus 2NL squared and cosine theta, let's call it beta, 1 minus cosine beta. So what you can do is to give this one the same term, 1 minus cosine beta and 1 minus cosine beta again, all by itself. So you can combine those two terms, they're retained together, and only at the top. And you will see this will happen to be 1 plus cosine beta and 1 minus cosine beta multiplied by NL squared, if you do the math right. Okay? Why? Because this is a 2. You can pull this out. NL squared, this is a common term. So you become 1 minus cosine beta plus 2 cosine. This will become this bubbles, the IE only increased by √2 of that, or you need to quadruple n to get double the IE. So if we put a real polymer, dissolve it, measure it by, let's say, light scattering or osmotic pressure, we will find this is actually not 0.5. It's wrong. It doesn't mean I'm going to lose my job. I'm still going to teach you guys. But I will explain exactly why that's not 0.5. That's really comes from the fact that our free joint chain, free rotation chain, all didn't consider the random walk, right? It will consider random walk, but didn't consider excluded volume effect. So in the Tim Lodge's textbook, if you read the chapter 6, there's a last part of it. If you go to the last, maybe chapter 6.7 or 6.10, it discusses about this effect. The polymer scientists actually call it self-avoiding walk. In the self-avoiding walk, I can do random walk, but I'm going to put a mark there, and I cannot go back to the same spot if I walk again. Then I cannot go back this. I have to go sideways. Then whenever I step on that, I cannot go back that again. That is a more realistic model. Why? Because that represents polymer is occupying space. You cannot wind back. So I'll tell you exactly what's the answer for that. So if you measure a real chain, your end-to-end distance will be proportional to n. To be exact, it's going to be 0.589 L, or typically people just call it 0.6 L, okay? Closer to 0. What's the difference between this real versus this idealized chain? We see it has a stronger dependence on number of bonds in the backbone. It's increased the dependence from power of 0.5 to power of 0.6. Is it significant? Yeah, hell yeah. This is a lot stronger dependence on the size of your chain. If I give you a real example, if your degree of polymerization for the past few example we have shown can be ranged about, maybe let's call it a thousandth, okay, dp for polyethylene. If we use a real chain, RE real divided by RE ideal, that's going to be n 0.6 L square, oh, sorry, no square, n L. So that's going to be n power of 0.1. I don't have a calculator, but if you do that, you will see this is a fairly big number, n power of 0.1. Okay? So that means real chain is going to be swelled, and it swells bigger as your chain is growing bigger because of self-avoiding walk effect. And this gives you some understanding of how the polymer single chain should behave. Okay? Any question for this part so far? So otherwise, we're going to probably wrap up today's class regarding this a little bit more realistic chain. So we got some homeworks for everybody. So I posted on the Canvas. Can you go to that and work on that? I'll update the due days. Typically, I would like about a week from the date of the meeting. So it will due next Tuesday. Okay? You can bring a physical copy, or you can send in the Canvas, or you can scan the email to me. I don't have preference, but make sure you put name on there so I can see who turned it in, okay? Otherwise, thanks everybody's attention.